The first of your extended break lessons is going to be a review of accumulation, also known as integral as a net change. Accumulation is an adding up of something. Hey, the accumulation of rain outside my door is pretty big because it's been raining so much. So the easy objective is the first one, solving application problems using integrals to find a net change from a rate. What I'm more worried about is, can you find the text clues that indicate we're talking about an accumulation problem? Hopefully we'll cover all of that before the end of the video. When you read this problem, you may not be thinking calculus. I think everybody thinks, ooh, 12 pages per minute. How many pages are going to be printed in 5 minutes? That's super easy, 60 pages. You're probably thinking, okay, how about 12 pages per minute? And then we'll do dimensional analysis to figure out we had to multiply. Minutes divide out, and we get 60 pages. And that's a great thought. That's something that's going to help you decide if that made a ton of sense to you. Hey, we're talking about using integration to get an accumulation. Although I did want to talk about using a graph to show. So let's think about what these axes are going to be labeled in. Well, down here, definitely minutes. Probably need a 5. And then the vertical axis, pages per minute. And then what would our graph look like? That would just be a horizontal y equals 12. Or maybe y. I don't know if y is correct. That didn't even look like a y. So how could we get our 60 pages printed out of this graph? How about the definite integral from 0 to 5 of 12 dt? That would still be what? 12t evaluated from 0 to 5. So 12 times 5 minus 12 times 0 still gives us 60. But printers don't print like that. Maybe your printer has to warm up, so it has a different rate for that first minute, say 5 pages per minute. And then for the rest of the time, that printer is still printing 12 pages per minute. So I suppose the question is, can we still use the area under this curve? I know straight lines aren't curves. Can we still use this area under the curve to figure out the total amount of pages printed in 5 minutes? Well, sure. So you could box this off. This rectangle on the left is 5 pages per minute times 1 minute plus 12 pages per minute times 4 minutes. We can just add all that together and get total number of pages printed. We're not going to do much of a graph, but we're still going to have the vertical label of pages per minute, the horizontal label of minutes. And then does this, I don't know, is this even possible? You have all these different rates. 8 pages per minute, 3 pages per minute, 11 pages per minute, 3 pages per minute, and 7 pages per minute. I guess the question is, what would all this area, doesn't really matter what numerical value, but what information would it give? Again, if we're talking about pages per minute multiplied by minutes, we're going to get some number of pages. So I guess what I'm trying to say, or trying to motivate you to think, is it isn't just necessarily area under a horizontal line. We've broken that into smaller and smaller pieces. So the next idea, I suppose, is calculus. What if we had this rate? 3 sine of pi halves t plus 5 pages per minute. Well, again, I think the most important thing is labeling these axes. That's going to tell us what sort of math to do. So horizontal axis is measured in minutes, then pages per minute up here. So that's 5, maximum of 8, minimum of 2. And R of t looks something like that. Now, it doesn't exactly matter where 5 time equals 5 is. Let's say it's there. Question is, well, how do you get that area? And if you could get that area, what would it mean? Well, that area is still measured in pages per minute multiplied by minutes. This is some number of pages, where the area represents some number of pages. How would you get that area? Well, it would simply be the definite integral from 0 to 5 of R of t dt. All you have to do is type that into your calculator. I suppose we can't type in what I just wrote. We'd have to type in 0 to 5, 3 sine of pi halves t plus 5 dt. I'm not going to worry about that numerical value. I think it's 26 something. But what I'm worried about is, do you understand why the area under this rate graph gives us the number of pages printed? The rate of consumption of rice in a country starting in the year 2000 is modeled by C of t is 3.7 plus 1.1 to the power t million bushels per year. How much rice was consumed from the beginning of 2004 through the beginning of 2008? You don't need to do this problem graphically, but I really think a graph helps explain what's going on. Now, the other thing I think we need to understand is you should already know your answer. Blank million bushels of rice were consumed blank. Okay, so that's pretty straightforward. We're given a rate measured in, it says million bushels per year, but I'm just going to write bushels per year. And then our horizontal axis, I'm going to write years even though it's years after the year 2000, meaning we're talking about 4 through 8. Well, what does C of t look like? C of t looks something like this. And the important part is our answer is measured in millions of bushels, not a rate. And we're given bushels per year, which is a rate. And bushels per year is the rate of change of these million bushels in the answer. So already you might be thinking antiderivative, but let's go ahead and think area from 4 to 8. Well, that would be an area measured in bushels per year times years. That would just be bushels. So how are we going to get this fill in the blank answer? We would be doing the definite integral. That gives us area from 4 to 8 of C of t dt. Or the definite integral from 4 to 8 of 3.7 plus 1.1 to the power t dt. We're going to skip that one. Okay, water is pumped into an underground storage tank at the rate of 8 gallons per minute. Water is leaking out of the tank at square root of t plus 1 gallons per minute. Looks like the leakage is getting bigger. At t equals 0, there are 30 gallons of water in the tank. So, first question, how many gallons of water leak out of the tank in the first 3 minutes? Let's go back and let's circle some things. So what do we need? So 8 gallons a minute are always going in. Square root of t plus 1 gallons leak out. And at t equals 0, there are 30 gallons of water in the tank. Do I need to use all of those in this part of the problem? There are more parts. Nope. All we need is this. Let's see. Maybe we draw a picture. Here's my tank. And how much are we putting in? We are putting in plus 8 every minute. How much is coming out? That's square root of t plus 1 gallons per minute, and 30 gallons to start with. Okay. So hopefully you can see the only thing that really affects how much water leaks out of the tank in the first 3 minutes is going to be that square root of t plus 1. Well, that's measured in gallons per minute. I want gallons of water, so I want gallons per minute. So this is gallons. Ooh, this is ugly. I'm not on my normal setup. This is gallons per minute multiplied by dt. dt is a tiny change in time, so that's a change in minutes. Definitely gives us the gallons we want. Okay. And this is an indefinite integral for now, but we're going to have a definite integral from 0 to 3. Okay, I'll let you work on the calculus there. Just put that into your calculator. Same question, or same setup, different question. How many gallons of water are in the tank at 3 minutes? Well, does the amount of water pumped into the tank matter? Sure does. Does the amount of water that leaks out matter? Sure does. And does how much water we start with matter? It sure does. So how many gallons of water in the tank at t equals 3? So that's going to be, let's think, starting amount. And to the starting amount, we're going to add the amount added. We're going to subtract the amount leaked out. Okay, the starting amount is easy, 30, and because we're talking about this time equals 0, I know the lower bound of integration is going to be at time equals 0. Okay, so the amount added is going to be measured in gallons. So right now that's 8 gallons per minute times a change in minutes, dt. And the upper bound is going to be 3 minutes. We're starting at 0. We want to know what's happening at 3. The amount leaked out, square root of t plus 1 gallons per minute times dt. Minutes. Okay. Write an expression for the number of gallons of water in the tank at any time t. That's actually pretty easy now because we did the last part. Normally that'd be pretty hard. So if it's any time t, I suppose I'm still starting with a 30, which means I'm still integrating from 0 to something. And that something has to be a t. So it's still going to be amount of water we started with, the amount of water pumped into the tank, minus the amount of water that leaked out of the tank. The only difference is these are t's. You know what that means about the integrand, the stuff inside these integrals? So the 8 is going to stay the same, but we can't write a dt. This upper bound and variable of integration can't match. So we're just going to change that dt to a dx or literally anything else. Right? Same thing over here. We want to write a t plus 1, but t is being used for something else. So we have to use a dummy variable x. So again, this 30 is the amount of water that started in the tank, the amount of water pumped into the tank, and the amount of water pumped out of the tank. Oh, leaked out of the tank. All right, let's see if you can figure out what to write here. Hopefully that looks awfully similar to the last question. The big difference is at time t equals 0, 0 gallons are in the tank. And luckily, the sewage isn't leaking out, it's being pumped out. Hopefully, to be stored somewhere else. I don't think we're supposed to just throw treated sewage into the trash. Okay. So at what rate is the sewage entering the tank at t equals 3 hours? How do we do that? Well, is that affected by this equation? Yes, in fact, it might even be easier than you think, because we're asked for a rate, we're given a rate, we're just supposed to evaluate E of 3. We're going to put 3 into that big equation and come up with, I think I can do this in my head. E of 3 is going to be 850 plus 715 multiplied by cosine of, 3 squared is 9, over 9 is 1, times pi is pi, cosine of pi is 0, so 815 gallons per hour. That was actually a pretty easy part of the problem, although I bet a lot of people thought you were going to integrate. Okay, how many gallons of sewage enter the treatment tank from 0 to 4 hours? Do we need to know that the treatment tank is empty at time t equals 0? Nope, we weren't asked for how many gallons are in the tank. Do we care how much sewage is removed from the tank? Nope, we don't care about that either. The only thing we care about is the sewage that is entering. So are we going to integrate? Let's decide. E of t is measured in gallons per hour, and our answer is supposed to be in gallons with an input of hours. So it doesn't really matter what E of t looks like. We're thinking area under this curve, because if we did graph here, you'd have gallons per hour multiplied by hours gives us total number of gallons. Okay, so we're going to integrate from, fill in the easy one, 0 to 4 of either, I'm going to write E of t. If you want to, you can write 850 multiplied by 715 cosine stuff. And don't forget that dt. All right, now the question you were waiting for. How many gallons of sewage are in the tank t equals 3 hours? Now this, we need to consider that the treatment tank was empty. We need to consider how much sewage is removed, and we definitely need to consider how much sewage was pumped out. So we'll think starting amount plus the amount entered minus the amount removed. So 0 to begin with plus the amount entered. We're going to have to integrate, and that's starting at 0 up to 3 of E of t dt minus another integral from 0 to 3 of 645 dt. Well, you don't have to do this. We were supposed to switch seats today, but I guess that's not happening.